So, how activation happens and how strong activations happens that makes the neurons lights up like this and detect the features and predict the output. So, as the input arrives here in the first layer or the input layer, like um, the pixels, like for example, here we use the convolutional neural network. Um, it will flow to the next layer, and um, s- and some of the neurons here in the next layer or the hidden layer um, activates because it detects some of its learned pattern. Like for example, this pattern, like here we see in the red, um, this one are here. Uh, the patterns are learned in this particular neuron. It detected here, that's why it lights up. And some of the neuron uh, doesn't respond or lights up because they didn't detect the pattern like this. The pattern um, here they didn't match. So strong activation needs a neuron and outputs a high value because the input strongly matches its learned patterns. So each of the neurons has the weights or the learned patterns. So these neuron patterns expects values, whether it's high values, low, high or low or moderate. So we compute the weighted sum or the match score. Um, Remember, neurons consist of multiple weights that connected to the previous neurons or layers. Um, Here's the interpretation of Z when we calculated the weighted sum. If it has the strong match, I mean, if it is a large positive, means it's a strong match. The near zero, weak match. And if it is negative, mismatch. Which means if the near zero, the patterns um, may contributed to the learned pattern in the neurons, but some of them isn't. That's why it's weak. Negative mismatch. It means it doesn't detected any sign that the particular learned patterns are there in the input features. So, what's the match that we're talking about? Like for example, the the weights or the learned patterns is like this one. The patterns is uh, large and low, and the neuron. I mean the input feature that you fed into the inference. We are validating here. Uh, let's say it fed into the neural network this particular value 9 that isn't trained or it is unseen data during the training. Um, say um, 6 and 1. This is high and this is low. So they match, right? That's why it produced the positive value. And its bias is 0. That is that is the parameters learned during the training. That is fixed. So the first pattern is high, the second low. So it's a strong alignment. So high Z, positive 5. So now we have the bias shift. How is it to activate? Like we have the bias negative 3. The value that comes up here, it detects, but when it comes to the bias is another things. So But it's still positive but weaker because of the bias. So what does the bias actually does? It shifted the the neuron, saying that uh, this neuron is uh, n- not so important. That's why I need to moderate it and adjust it to its to lower value, because we don't want it to become too much um, high. And then we apply the activation function um, to the z. So most common we use is ReLU. Um, if it is um, not less than or equal to 0, then the values will still remains like this. Is equal to 5, the activation function is 5. And we use the ReLU or the activation functions to produce a nonlinearity. So let's focus here and how this strong activation functions uh, used in activations. So if it is positive, it will fire strongly. And if it is a weak activation, zero point 0.5, it is a weak signal like this. It does not light up so much. And an activation, if it is equivalent to 0 or less than 0, that's completely off. So strong activations, the neuron is highly confident that its learned pattern exists in the input. It means that the neuron's learned pattern is clearly present in the input, producing a high output that strongly influences the downstream computation. So you can think at the neuron is a pattern detector that with this low output, it means that I don't see it. It is a medium. Maybe that uh, the the patterns are there, and if it's high, yes, this pattern is clearly present. So strong activation happens when it's a good alignment. Input matches with patterns, large input values, strong signals amplify results, and the helpful bias make activations easier. So if the helpful bias, if the bias is positive, it makes the activation more easier because it adds up to the positivity contribution. So let's compare how the strong versus weak versus none. So let's say we have the neuron one and negative one, and we have the bias of 0. So it expect that high and low. Um, let's say the input A um, has these values, large and low. That is aligned with this one. That's why it has the value, the strong activation 9. This one, uh, 3 and 2. It's a partial match because the neuron expect that um, this one is high and this one is low, but they are relatively nearly to have the same values. That's why the z-score activation is 1. And the input C is mismatch. Let's say we have low and high, but we expect high and low in the activation. So, and then across the layers, the strong activation that is separated in one neuron. The strongly activated neurons pass strong signals forward, pass strong signals forward like this. Um, it will act the same. It is the neurons in the previous layer, and this is the layer that has a neuron. It's saying that this one's fires up because it detects the loop like this here. So it means fire. That's why it fires up. and this one fires up because this one holds the patterns of this one. So we calculate the weighted sum of this one, the input features, and the the the, the learned patterns, and it's detected this one, and the rest doesn't fires up because it doesn't detect its learned pattern. The next layer combine the signals, like what I've said, and this builds simple pattern complex planner. And the final decision. The final decision is um, 9 because these learned patterns here in this final layer is completely just one. It's actually the the pattern of this one, the pattern of 8, the pattern of 7, the pattern of 6, the pattern of 5, the pattern of 4, the pattern of 3. It's a completely whole. So it detects uh, in the previous layer that it matched their pattern. That's why it produced the 9. And it um, those have the tiny scores here that relatively small. And those scores are called logits. And those logits will be converted into the probability to the percentage of probability using the softmax. So let's talk about the strong activation furtherly, like um, the perfect alignment. Like um, we're talking about this one. The what is alignment? So alignment is important features in the input. In the input are strong, where the weights expect them to be strong. Like for example, this one. Um, we have the expected the input features of 213, and the weights or the neural weights 9, or the learned patterns 312. It has the strong um, activation because it's a large value, because they match the alignment, they align together. 213, this is high, this is low, this is high, this is high, this is low, this is high. As you can see, they are proportional equivalent but in the different order, like that. So the input H is a weight, is a contribution. So it means to multiply it together. To multiply it, so um, we could find its matches, positive, negative, both negative and negative will be positive, positive and positive becomes positive. So this one is high and is high. So meaning is strong. This is a medium and medium. As you can see, you have the same patterns. Medium value. This they are aligned. Um, high value and high value. This is strong alignment. So what's happening? Whereas the weights are large, inputs are also large. That is alignment. Another example, this is misalignment would look like 131. The input feature is 131, but the neuron expected um, 312. As you can see, the pattern of 312 is high, low, medium, or low. So the input features is a 1, but the weight is 3. Um, it should be high. This one should be high, but it's low. Its contribution is 3. So the input is 3, but expect this low. Not very important, but high. So less aligned is lower score. So you could think it. as a weight is high, low, high, like what I'm using while I'm teaching it, like high, low, high, those like that. So why alignment gives high score? So this is a summation of the weighted score. So high times high, it give big positive. Low times low, it's small. High times low, it's weak. Okay. So yeah, this is another example of loose alignment and passive contribution. So like for this example two. So we have the weights of 1, 2, and 3, and the input values is 0.51 and 1.5. They're not aligned, but um, I mean they are aligned because the weights is um, this high, this is low, this is high, this is high. As you can see, this patterns also as much to it because this is low, this is high, and is high like this. So this is still a strong match. So um, like this is a contribution. That's why we use the summation here. Each those features or patterns adds up to the final results. So positive contributions supports a pattern, and negative contribution contradicts the pattern. If positive dominate, then z is greater than zero, and if z is greater than zero, that's a good match. And if negative dominates, as like z is less than zero, z is less than zero, which means mismatch. So there's a tons of examples here. Like for example, if we have the inputs 1 and 0, um, it's a large and low. This is wrong because the weight expects that high and low, same patterns, larger scale. How about this one? The weights or the neurons expect the value of low and high. It's still a strong match like that. So if we have 2, -1, and -1, so the neuron expect that it's high, low, and low, but it's contradict. It is low, high, and high, but we want the neuron expect the pattern of high, low, and low. Others dominate. So we could notice that positive Z more agreement, pattern satisfied negative Z more disagreement, pattern violated, and near zero mixed contributions and weaks or unclear. So in the end, we add the bias. What is bias? Bias shift the results. It can turn weak to the positive or positive into the negative. Bias control how evidence is needed before the neurons fires. Positive B or positive bias, it will fire easily. But if we have the negative bias, um, it still it means it still need a strong evidence or large value. It adjusted during the training. That's why it's the way they are. Uh, the reason why the bias is negative because it's bring an strong evidence of a pattern before it fires up. Each neuron has its own bias and it can be positive, negative, or zero. There is no restriction it learned during training. So positive bias easier to activate, like this one. If we have the weight times features one, and we have the bias two. So even a small match becomes strong. Neuron activates more easily. Like for example, if we have negative bias, it's harder to activate. Like um, we multiply the if we have this one, even though we have the pattern match here, um, it still appear the low value because the bias is negative because it's saying that this pattern must be a strong score value before it activates. If even a descent match might not activate, neuron is more strict. That way. So as we discuss the flow or the activations here, um, as we can see the pattern from a layer from the first layer, hidden layer up to the last layer. Um, what it does is it's only a combinations of the patterns as as the new as the layer goes deeper, the more patterns becomes clearly. That's why um, in the last layer, it has this kind of um, pattern. That's why it detects this one and produce the logical score. So as the final layer combines feature and the decision. So like what I said, earlier layers learn the basic complex features like strokes, curves, loops, like that. And the last hidden layer, the output some things like h equal h sub 1, h sub 2, h sub 3, h sub n, where h sub uh, I determines how strongly the the feature is is present. How strongly the feature is present. How this these features are present here in the last layer. So the final output layer, like for example in MNSD, this one is has a data of the 10 classes that we use from 0 to 9. It has 1,000 of images of the handwritten data. So each neuron computes z sub z sub k equivalent y w k w sub k times h plus b sub k, where k means the class from 0 to 9. So we have the 10 classes. And h is the features from the previous layers. So we have the 16 h features from the previous layer. Okay. So each output neuron, each output neuron basically is basically saying that if this feature like 9, this one 9 appear together, I think it's digit 9. If this one appear together, it's digit 9. If this, like for example in 8, if these features here are appear together like 8, um, I think this is digit 8. Let's say the examples, let's say the features um, 9. So we have the loop, vertical line, and bottom curve. So digit 9 might learn during the training. Uh, it learns the pattern 3, 1, 2, or high, low, or medium, uh, high. So meaning loop is very important. Vertical line somewhat important, but the bottom curve is important. So if those features are strong, then there's a high scores. So how patterns contribute? Each feature contributes weighted evidence to each class. Think of like this: hidden layers detects pieces of patterns in hidden layers, but the output layer combines them into full meaning. So what is uh, um, about? So this name. So suppose we have the input features, which is 2, 1, 3, high, a medium high, low, and high. And but the digit 9 neuron um, um, expects that it's high, low, medium, high. So to calculate it using the weighted sum, um, 3 times 2 6, 1 times 1 1, 2 times 3 is 6. So it's a positive contribution. So and digit 1 has like this one, expect low, high, and low. But the input features appear here is 213, which is high, low, high. And it matches into the 9. Even though it receives the the positive or uh, strong evidence, but the digit 9 has a lot of positive contribution than this digit 1. So it might appear that digit 1 has only um, uh, detects this one, this um, this straight line. That's why it still has score. But the digit 9 neuron, all of the features is matches. So the result is 9 higher score than any classified values here, logic scores here. The 9 dominates, though the prediction is 9. And then the softmax converts scores into probabilities like 0.01. Like for example, the 0, its probabilities is 0.01 and 0.02. And the 9 is 0.92% that it is a 9. So the highest probability that's it will choose the correct answer, the right answer that is predicted. So the value is 9. That's why um that's how the convolutional neural networks activate the functions and turn it to the predicted value, and that's it.